Hello, universe. Interesting problem today. We're looking at a curve gamma from some interval I into space R3. We want it to be a regular space curve, which means its derivative is non-zero in magnitude. Okay, so it has a non-zero derivative. It's parametrized by arc length, so not only is its derivative non-zero, but in fact, its derivative always has unit magnitude, okay, unit speed, all right? So this is my puppy strategy. Okay, so now we're assuming that the second derivative is non-zero, and we're defining the tangent vector to be the first derivative, gamma prime of s. We need to prove that the second derivative is orthogonal to the tangent vector. That's part A. Next, we're going to define this n to be the normal vector to the curve, and it's the unit vector gamma double prime of s divided by its norm. So it's basically the unit vector in the direction of the acceleration of gamma. Then we're defining the curvature to be the length of the acceleration, okay, so the magnitude of the acceleration, okay, so n is a unit vector, and then the length of t prime is going to be kappa, the curvature of our curve. And then part C asks us, we define a unit vector b to be t, the cross product of t with n, okay, so right-handed rule of here's t, here's n. The vector b is going to form a right-handed frame with t and n, and it's called the binormal of the curve gamma. And these three vectors, t and b, form an orthonormal basis, and it's called a TNB frame. The reason why it's called a frame is because it's a smoothly varying basis for the tangent space at every point in the curve, okay? All right, and so we're asked to prove that the derivative n prime is negative kappa t plus tau b, where tau is some real number which is called the torsion of the curve. And there's actually a part D as well, but I'll get to part D once we solve these problems. Okay, so for part A, we're going to observe that the norm of t of s by assumption is always 1, okay? So if I look at the inner product of gamma double prime and t, this is just the inner product of gamma double prime with gamma prime, okay? The t tangent vector is the derivative of the curve. Okay, but now I can recognize this as actually the derivative of 1/2 the inner product of gamma prime with itself, okay? And this is by the product rule. So the product rule tells me that, that if I expand this derivative, then this is going to be, note that this is going to be the derivative of the first argument, inner product with the second. So this is 1/2 gamma double prime inner product with the second plus the derivative of the second argument, inner product with the first, so gamma prime inner product with gamma double prime, okay? All right, so essentially this is just the product rule using for inner products of vectors, okay? All right. Okay, so now we know that this inner product of gamma prime with itself is actually just a constant, namely it's 1, because our curve is assumed to be a unit speed parameterization. So therefore, the norm of this vector is a constant 1, and so its derivative is 0. It's unchanging with respect to s. So what we conclude is that is that the inner product of gamma double prime and t is 0, therefore they're orthogonal. So that proves part A. Okay, now let's look at part B. Okay, so we're defining n to be the unit vector in the direction of the acceleration, and then we're defining the curvature kappa to be the derivative of the tangent vector. Now, this isn't really a question, this is just a definition, so there's nothing to prove here. It's probably a typo in the book. The book, by the way, is Differential Geometry by Loring 2. Excellent author, excellent book, highly recommended. But yeah, so this isn't really a question, this is more of a definition of curvature, okay? So let's move on to part C. Okay, so B is defined to be the cross product of t and n. It's the binormal vector. We need to prove that n prime is equal to negative kappa t plus tau b, okay? So, first of all, this notation suggests that n prime is orthogonal to n, okay? So the first step is we just need to look at the inner product of n prime and n and try to show that it's 0. If we show that this is 0, then we can conclude that n prime must be within the span of t and b, because t and b form an orthonormal frame, right? So let's look at this product here. Okay, so again, this is going to follow from the fact that n is a unit vector. It's the same logic as the previous problem. I can write this as d over ds of 1/2 inner product n with itself. This is again by the same product rule, okay? And now, well, this is just 1, right? Because n is a unit vector, so its length is constant. So in general, if you have a curve whose speed is constant, then the acceleration of that curve is going to be orthogonal to the speed. Okay, and in this case, yeah, if you have a moving vector along a curve, then the derivative of that vector field along a curve, if the vector is constant magnitude, the derivative must be orthogonal. Let's draw a picture here. So if I have a vector field along a curve, and that vector field, all the vectors have the same length, unit magnitude, then the acceleration is going to be, or the derivative of that vector field, if I take the derivative of that vector field, it's going to be a new vector field that's orthogonal to the previous, okay? And that's just by this exact calculation, all right? Okay, so this proves that n prime is indeed a linear combination of b and t, because its projection onto the n vector is 0. Now we just need to show that the component in the t direction is negative kappa. Notice that tau is defined by this property, okay? So tau, once we show that the component in the t direction is negative kappa, we're actually done, because tau is defined to be the component of n prime in the direction of the binormal vector, okay? Okay, so now let's look at n prime inner product with t, okay? So notice that the derivative, d over ds, of nt, okay, well these are orthogonal always, so this is always 0, okay? On the other hand, if I use the product rule here, this is n prime inner product with t plus n inner product with t prime. So what this tells me is that the inner product of n prime and t is the negative of the inner product of n with t prime, okay? All right, and so now we're on a good track here. The cat is doing some stuff. Get your head out of there, Blue. Get out of there. Get out of here. Come on. Okay, everyone say hello to Blue. He was causing problems. Say hi, Blue. Okay. All right. He's a troublemaker. So now, if we expand this expression on the right, well, we know that n, remember from the previous problem, t prime is defined to be kappa n, okay? So we actually know that by definition of kappa, this is just the following expression, and then the inner product is bilinear, so I can pull out kappa, and then this is a unit vector. The normal to the curve is unit vector by definition. So this inner product is 1, and we're left with negative kappa. Okay? All right, so that tells me exactly that n prime is going to be, let me just write it out explicitly for you so you can understand the logic here. So n prime is going to be the projection of n prime onto each vector in my frame. So t times t plus the projection of n prime onto b, or n plus the projection of n prime onto b is b, okay? And we've shown that this is 0, and this expression we've shown to be negative kappa. And so then we have the following result, and which is what we wanted, and we're defining this to be the real number tau, which is the torsion. Okay, now let's look at part D of the problem, which I haven't stated yet. Okay, so part D asks us to prove that the derivative of the binormal is negative torsion times the normal vector, okay? So by definition, the binormal vector is the tangent cross product with the normal. And if you unpack the definition of the cross product, which is the determinant, let's say, following determinant, x, t, y, t, z, n, x, n, y, and z. So if you unpack this determinant formula, then what you're going to get is something like, okay, let's just look at one of the terms, t, y, and z minus n, y, t, z, I hat, plus dot, 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 okay? So that's just the direction in the I hat direction. But I'm just making a point that if I take the derivative of this quantity, then this derivative is going to hit t, y, and n, z, and we're going to have to do a product rule here and a product rule here. And the structure of the of this formula we preserved, everything will split apart across the product rule, and we're going to end up with a product rule for the cross product, which is just b prime is t prime cross n plus t cross n prime. Okay, so now looking at this formula, we have that t prime, by definition, is the curvature kappa times the normal vector n. This is the definition of n, okay? And so here we have n cross n multiplied by the curvature. Well, any vector cross itself is 0, okay? So this first term is going to go to 0. The second term, is t cross n prime. Now we solved in the previous part of the problem that n prime was negative kappa times t plus the torsion tau times b, the binormal vector, okay? So the component in the direction of t is going to go to 0. against this cross product. Note that the cross product is linear over this addition sign, so it'll split over the addition sign, and then t cross negative kappa t is 0 because t cross itself is 0. Kappa is a constant. So this is just going to give me tau times t cross b. Okay, and then notice that that t cross b. Okay, so if we look at TNB, this is going to form a right-handed frame. Okay, so this is an orthonormal frame, right? We've already established these two vectors are orthonormal, and then this vector is the cross product of these two, so it's certainly orthonormal to these other two, right? And they actually form a right-handed frame. Okay, so in particular, I noticed that since this is a right-handed frame, any cyclic permutation of these quantities is going to give me equality. So I guess the cyclic permutations of this expression tell me the values of these cross products. Okay, so let me just explain what I mean by that. What I mean by that is if I perform cyclic permutations n, b, t, so picture just rotating all of these letters, shifting them all to the right by 2, and then if I shift them all to the right, okay, b, t, n. Yeah, so if I shift t and b to the right by 1, and then I get btn, and then shifting btn to the right by 1, where I put n at the beginning of the rotation, I get nbt. Okay, so these are what's called cyclic permutations. You can picture t, if you're not familiar with this idea, you can picture t and b being on a circle, okay? And then essentially think about rotating this circle. So if I rotate the circle, let's say by 120 degrees, I'm going to end up with b t n like so. And so you see nbt, that's one of the cyclic permutations. And then if I were to rotate this circle again by 120 degrees, I would end up with TNB. Okay? So these are the cyclic permutations. And notice that the key is that because these form a right-handed frame, then I get the following equalities. Okay? It's kind of a nice way to remember how the cross products of my orthonormal right-handed frame are defined. Okay? And so this is the reason why this is true is just by convention. Remember, the cross product is antisymmetric. So this is negative tau b cross t. And then we just choose the direction of our frame to be right-handed. So at the end of the day, b cross t is just negative tau n. Okay? We're done right now.